Greetings, welcome to a tutorial for lab number 4. It has two parts, 4.1, 4.2, 4.1. We talk about RC, we have only one C, it's a first degree system. 4.2, it is an inductor, and we are going to see different waveforms. I'm going to talk about it. You need one capacitor. Capacitor is a box that you would see it on top of the desk. You need microfarad. First of all, it is capacitance, microfarad. Already whatever you see on this is going to be microfarad, and they are available on these two red. Plus minus, minus plus really doesn't matter. The polarity is not defined by the component, so don't worry about the polarity. And when I say I want to have 0.1 microfarad, it's already 0.1, and this is 1. So it's going to be 0.1 microfarad. That's the way I'm going to set. Make sure everything else is 0. That's the capacitance. When I get to the inductance, the word inductance is on top. The unit is going to be Henry. The two red pins still applies. Again, the polarity, it doesn't exist until the external force determines what the polarity is going to be. Now, we are going to need 0.5. This is 10 minus 1, 5. That's going to be 0.5, 0.5 Henry. So I'm going to utilize this. This is 0.5 Henry. Now take a look at my circuit. There is a slight modification that I need you to be aware of. A resistor is on top, capacitor are internal. This red area is actually the function generator. And that R internal is internal to the function generator. It has a 50 ohm input impedance or output impedance for the next stage. So what I'm saying is that you don't need to put the 50 ohm into the design. It's already, 50 ohm is already inside the function generator. You have a resistor that's going to be 1K, and then you have a capacitor, 0.1 microfarad. And then what happens? I have a function generator. Why am I using a function generator? The theory we discussed inside the classroom, you need to have a unit function, a step function. But the problem with unit function and step function is, as soon as the drastic change happens, you're going to lose it. All is said and done, finished. And since it's going to happen so fast, we won't be able to actually study the behavior of the design under such a circumstances. And that's why we can't just say unity function or a step function. We need to actually do a kind of a square waveform. So this square waveform is the function generator. When you turn on the function generator, note that it is going to be initially set to the triangle waveform. You need to make sure it's a square waveform. You push the proper key. Now, I intend to have this frequency set in such a way that it actually gives enough time. I'm going to make this as long as possible so that the circuit thinks it's only a unit function. The circuit thinks, oh, it's flat, and it's going to respond to that flat incoming DC signal. So then it's going to come down, then it's going to be another flat, then it's going to go up, another flat, and it goes on. I'm going to make sure it is wide enough to allow all the changes to take place inside the design. Now, if you remember in the given RC design, there is going to be a special waveform. The special waveform, I'm just going to go ahead and show you what you are supposed to see. You are supposed to see a special waveform which is going to go exponentially into a steady state response. Then it's going to go, and this point is going to fall off because a new excitation has entered into the equation. So it's going to come down. I'm going to widen it enough so that everything goes into a stable state, and it goes up like this. So please make sure that you see the flattening on the rise time, the flattening at the fall time. You need to see the flattening, that's going to be an indication of a steady state response. Now, in RC scenario, if you remember, or RL, doesn't matter, because it's a first degree design, it follows a very easy equation. Y of t, a given variable, voltage or current, specifically in this case voltage of the capacitor, for example, is equal to y of t is equal to y of infinity plus y of 0 plus minus y of infinity e to the power of minus t over tau. And tau is my time constant. I need to know what is my y of 0 plus what is my y of infinity and what is my tau to be able to actually represent this using equation. Remember I said that we are going to widen the frequency, we are going to widen the signal in such amount that actually it goes and it becomes a steady state. So when I take a look at this, what happens? All the charge on the capacitor has discharged to 0. So if I take a look at this, for example, at 0 minus, I'm going to have 0 charge. At 0 plus, I'm going to have 0 charge. So basically, Y of 0 plus, in this case the voltage, I mean voltage of 0 plus is the same as voltage of 0 minus, is the same as 0 volt. I'm asking you to focus on this point. As you let it go to the infinity, from engineering point of view, you can see what happens. The capacitor is going to take up all the charges that are possible to take, and therefore the charge is going to stop. No more charge is going to come in to the capacitor. When we say there is no more charge to come in, the flow of people coming and sitting on the plate is going to stop, and therefore this current is 0. When I say 0 current, I mean open line. This capacitor is going to act like an open line. If this red signal, this is E, and this has been left E for a long time, this is going to charge up. The current is 0, the voltage drop is 0, the voltage drop is 0. If this is E, it dumps itself across the capacitor, and therefore Vc of infinity is equal to E. In order to find the tau, I ask you in the class to stand across the capacitor, look at the design, and tell me how much R equivalent is. Now, in order to do that, you were supposed to shut down the independent source to 0. This is a voltage source. You shut it down to 0, and it becomes a short line. So this one is going to be a short line. Now, you are observing from this angle, and you can see R and R int are going to be your R equivalent. So R equivalent is R plus R int, internal. In this case, for example, 1000 plus 50. So it's almost 1050 ohm. C equivalent, I don't have too many capacitors. I have only one capacitor, and the value is supposed to be 0.1 microfarad. 0.1 microfarad, which means 0.1 times 10 minus 6 farad. Micro means 10 minus 6. And what is your tau? Your tau is going to be R equivalent, C equivalent. So this is going to be 1050 times 0.1 times 10 to the power of 6. You can see how much that value is, and that would be in seconds, because you make sure all the resistors are in ohm, all the capacitors are in farad, the original unit, and that's why the tau is going to be in the original unit, which would be in basically seconds. Of course, there are going to be some variations of this. When you say 1000 ohm or 1 kilo ohm, it's not necessarily as so, because there is tolerance involved. When you say 0.1 microfarad, there are some tolerances involved. So obviously you are going to have a bit of an error just because of the tolerances, but more or less you're going to be around this when you do the tau calculation. So what is my function? My function Vc of t is equal to Vc of infinity, Vc of 0, and then e to the power of minus t over tau, you just calculate. The first objective of lab number 4, work 4.1, is to actually verify that this is indeed exponential going up, exponential coming down. You are going to actually find Vc for going up and Vc for coming down. The difference is, when it comes down, your Vc is 0 plus now is E. Remember that? Because your axis has shifted to this point. Vc 0 plus and 0 minus is going to be E. Vc of infinity is going to be 0. Vc of 0 plus E, Vc of infinity 0. Tau is going to be the same. Tau depends on the topology. You haven't changed the tau, and therefore you can actually utilize tau. You calculated it. Therefore you have a function for this, and you have a function for that. That's one thing. How am I supposed to verify tau? I'm going to explain that in a bit of a detail. Inside the classroom, we discussed how much tau is. This is a rising signal. So that's, generally speaking, y of t, and the rising signal is exponential and actually coming down to this. What do I have to do? This is 0. First of all, I make sure that the proper reference is actually in place. So I know that this is indeed 0. Now I'm going to find this gap. This is Vc of infinity. This is Vc of 0 plus. Remember, Vc of 0 plus may not be 0. Well, just play with the scope, but you can see what I mean. The difference is going to be the alpha, the gap between a steady state response and the initial value. Now, according to calculation we carried out, this is you need to find 0.63% alpha. You don't have to convert this to volt or amp or anything in terms of experimentation. All you have to do is to count the units, and then 63% of those number of units is going to give you here. Then you are going to come in, hit the red curve, and come down. This is your tau. This is supposed to be almost the same as what theoretically tells you to be. The higher the tau is, the longer it takes. It means that in order to reach 63% of the gap, I need longer time to reach. So it's going to be slower. The shorter the tau is, it means it's going to be faster. So 63% is going to be here, and then you are going to actually reach the saturation or a steady state response relatively fast. That's the rise time. Now, there are also possibility to actually calculate tau theoretically on the fall time domain. Let me actually go in and explain what the fall time is, how you can calculate the fall time, tau from fall time. This is my signal, and this is y of t, and your signal happens to be actually coming down. So this is your perhaps Vc of 0 plus, and this is going to be your Vc of infinity. And by the way, this alpha is absolute value of Vc of infinity minus Vc of 0 plus. It really doesn't matter this minus this or this minus this. All I need is a gap between the initial value and the final value. The same thing is true here. I'm going to find the gap between the steady state response and the absolute value of Vc of 0 plus minus Vc of infinity. That's going to give me the gap. Now you need to find 63%, this time not from the bottom to top, but rather from the top to the bottom. This time you're going to find 63% of alpha this way. Then you're going to come in, hit the curve on the red, you come in down, this is going to be tau. Theoretically, that's possible. Practically, it's not. Why? Because this point, when you look at the scope, it's deceiving. It might be here, but actually it might have started a bit sooner than you might imagine. Why? Because of the sampling. The sampling that happens is going to miss a few samples, and that few samples, because it's a very sharp change, you are going to miss it. So the actual signal Vc 0 plus might be here actually. And that's why I do not recommend finding tau on the fall time. Always take a look at this and find the tau on the rise time. So please, rise time, focus on the rise time. Make sure you have opened up the signal wide open. You can see perhaps the entire screen of a scope is actually going to go and dedicate itself to the signal. Now, this is our C approach we did. And in terms of RL, I want you to follow what the lab manual says. The only difference is plus minus, that's going, I'm sorry, this is going to be a square waveform. Of course, for a short period of time, I'm going to say plus minus because it's supposed to be DC. That's going to be flat. This one is going to be resistor, and that's going to be R, and this is inductor. Okay? Remember, the voltage of a capacitor doesn't change drastically. The current of an inductor doesn't change drastically. So I need you to be extremely conscious about what you're trying to find. In this case, I'm trying to find IL of 0 plus, which is the same as IL of 0 minus. That's the value. When I want to find y of infinity, I mean IL of infinity, how much that is, and then finally tau. Tau for RL design is slightly different. This time it's going to be L divided by R equivalent. L equivalent divided by R equivalent. You put yourself across the inductor, you look at the design, still it's going to be R inch and R 1K. So basically R equivalent seems to be the same. You find your tau. Now, the way we treat the inductor is this. If we let the system go for a long time, the inductor is going to act like a short line, contrary to what the capacitor is. So if you let the system go for a long time, this inductor is going to act like a short line. You have a voltage E for that wide scenario, and you have R int and R. So how much is IL of 0 plus? Because you left it that far, for example. In this case, if you let it go for a long time, obviously you have E and you have let it go for a long time. Therefore, this is going to be E divided by R plus R internal. That's what happens. But initially, if E is 0 and you have let it go for a long time, once again, just before, 0 minus, 0 plus, that's the moment I'm trying to focus. If you say that this is 0, obviously this voltage source is going to be 0. It's going to be short. You don't really have any source of energy to produce the current that we need and we talk about in RL. And therefore, this is going to be 0. You've got yourself IL, 0 plus, IL infinity, and tau. You've got yourself the necessary ingredients to write the equations for RL. Now, in terms of tau, the same game applies, and this time we made a slight modification so that you can actually read the tau with confidence, because in last experiments, last few years, we had a lot of noise and nobody was about it. This time, hopefully, it's going to be a lot less noisy, and I appreciate your help and cooperation. Thank you very much. I hope you enjoyed this recording. Thanks a lot. Bye.